After completing the flight performance calculations, part of the aerodynamic forces is simulated. The pressure distribution over the wing surface has been obtained, providing a reference for further structural analysis. But before that, I still need to make a final confirmation of the appropriate airfoil selection. Since most of the previous calculations were based on the NACA 23012, there were some issues with the stall margin. In the previous video, the calculations were redone by switching to the NACA 23015. In this video, we will compare the basic characteristics of three airfoils. The conclusion will determine which one will be used for subsequent fluid structure interaction simulations in order to evaluate aerodynamic loads and structural strength. First, let me briefly explain the test environment. All three airfoil tests use the same incoming flow conditions, with V equals 30 meters per second. A consistent meshing method is applied. The calculations are performed by varying the angle of attack under the same setup. In the computation, a two-dimensional incompressible external flow, RANS, is considered with the SSTK omega turbulence model. Time advancement is carried out using both implicit unsteady urines and steady approaches in order to compare and identify the method better suited for high angles of attack where turbulence and vortex structures dominate. At small angles of attack, laminar separation on the wing's surface is not significant, and turbulence near the trailing edge is also weak, so the steady assumption can provide satisfactory results. However, at higher angles of attack, the observed residual and aerodynamic fluctuations are a physical unsteady phenomenon, namely the formation of separation bubbles on the upper surface and vortex shedding in the wake. In this case, the steady solution also exhibits periodic oscillations following the flow fluctuations. At high angles of attack, aerodynamic characteristics exhibit pronounced unsteady fluctuations, which often cause convergence difficulties. There are two possible approaches. The first is to use implicit unsteady with second-order time discretization, which can more realistically capture unsteady flow features and provide relatively stable results, though the solution will show periodic oscillations rather than converging to a single value. The second is to continue with the steady approach and apply a moving window average to smooth the results. This reduces computational cost, but only provides a numerical smoothing without reflecting the true unsteady nature of the flow. For this test, I use the second, simpler calculation approach. Here we can see the drag coefficient C, D, and lift coefficient CL results for the three airfoils. The drag coefficient is quite clear. It grows almost exponentially with increasing angle of attack. After mean optimization, the lift coefficient CL becomes more stable. It can be observed that the GA30U315 has better stall resistance compared to the other two. The CL max of GA30U315 reaches about 1.4, with the corresponding stall angle of attack around 15 degrees. The maximum lift coefficient also allows for a rough comparison of the stall speeds under these conditions, where the GA30U315 shows the lowest stall speed. After excluding the use of NACA 23012, GA30U315 may be used for the subsequent surface pressure calculations. Thank you again for watching. If you'd like to explore more from the Lavion Ideal channel or follow the insights shared from Lion, we warmly invite you to subscribe.